colleagues and close friends in the Egyptian Society of Nephrology for their kind invitation to this first-class meeting. And in fact, nothing is more prestigious than co-chairing a session with a president. So on behalf of Muhammad and myself, thank you, Mr. President, for being with us. Our first speaker for this session is Professor Richard Johnson. He was actually introduced last night, but I'll introduce him again. He's a professor of medicine and chief of the Division of Renal Diseases and Hypertension at the University of Colorado, Denver. And his main interest is uric acid, gout, and its relation to hypertension. He'll be talking about a role of T cells and autoimmunity in primary hypertension.
Thank you very much. Yeah, thank you. It's wonderful to be here. Yesterday I gave a controversial lecture about the role of dehydration as a possible cause of chronic kidney disease. And today this talk is also going to be controversial because I'm going to try to present evidence that high blood pressure may have an autoimmune component. So actually, the discovery of high blood pressure was made by a medical resident at Guy's Hospital in London, Frederick Akbar Muhammad, a Muslim physician, medical student, was given a research project where he was to measure blood pressure in the community. And back in the 1870s, there wasn't a really easy way to measure blood pressure. But a man named Marie, a Frenchman, had developed a machine that could measure blood pressure through a spring-operated instrument. This thing, which was called a sphygmograph. And he actually, Frederick Muhammad, was very resourceful, and he met with a watchmaker, and they made one of these machines. And for his research project, he went into the community and measured blood pressure. Interestingly, at that time, it was thought that high blood pressure was really a reflection of kidney failure. And most of the people who had high blood pressure were thought to have albuminuria and true kidney disease. But when he measured the blood pressure in the community, he found that many of these patients did not have albuminuria. And so he wrote about this and said that hypertension could be a feature in the normal population in the absence of proteinuria. And he was the first one to describe primary essential hypertension. Well, by the 1890s, the blood pressure cuff was developed by Rivarocci in Italy. And soon blood pressure began to be measured in the physician's office. Janeway and Cushing, two very famous American physicians, went to Italy and brought the blood pressure cuff back to America. There started to be a lot of studies about the importance of high blood pressure. By 1912, it was known that high blood pressure increased the risk for death from studies that the insurance companies were doing. And soon the measurement became a routine measurement made by the physician, and the blood pressure cuff became something that was carried in the little black bag the physicians took to see patients. Now, the original studies done between 1900 and 1920 looked at the frequency of hypertension in the overall population. And this was important because it was very important to the insurance companies. And interestingly, most of those early studies showed that hypertension was uncommon, defined as a blood pressure of 140/90. It was only seen in about 5% of the population of the adults. In some studies, maybe up to 10%. but never more. In a huge study performed in 1939 of 11,000 people living in the Chicago region, only 10% had a blood pressure of 140/90 among 50-year-old men. Today, it's around 30%. And so we've seen a remarkable increase in blood pressure in the last century among adults. Not only have we seen it among adults in the U.S., it has actually increased throughout the world. There were studies done in Arabia in the 1920s where hypertension was absent. In Iran, hypertension was absent. In Philippines, hypertension was only seen in about 5% of the population. In China, in Alaska, among the Australian Aborigine, among the Native American Indian, hypertension was less than 5% of the population in those early days. People don't realize it, but studies showed that hypertension was completely absent in Africans in the early days. It was like less than 1%. Today, hypertension is increased dramatically. By 2025, it is estimated that there will be 1.25 billion people with hypertension. It's the #1 cause of stroke. It's the #1 cause of heart failure. It's thought to be the #2 cause of kidney disease. It is a very important condition. It's the most common disease in humankind. It's the most common disease with one of the greatest morbidities. Now, why is hypertension increasing, and what's causing it? Well, over the last century, we've seen a rise in obesity from about 3% in 1900 among 50-year-old men to more than 40% today. In some countries, obesity has become such a problem. In the island of Nauru, 94% of the population are overweight or obese. In some countries, like Kuwait, more than 25% of Kuwaitis are diabetic right now. That's amazing, and it points out to the problem we're seeing with this epidemic of obesity and diabetes and hypertension. Now, when people were trying to figure out the cause of hypertension, it was noted by the French back in the 1890s that you could restrict salt and you could lower blood pressure. By 1920, Frederick Allen was implementing low-salt diets for the treatment of hypertension. And it became apparent that there was a general relationship where countries that were eating high amounts of salt were generally having higher frequencies of hypertension. And so there became the salt hypothesis for what drives hypertension. And by the 1960s, it was apparent that the kidneys had a key role in this, and that there was an issue where if the kidneys could not excrete the salt, the blood volume would expand and it would raise blood pressure because there would be an autoregulatory response where there would be vasoconstriction and a pressure natriuresis but at the expense of a higher pressure. The real breakthrough came from Louis Dahl, who in the early 1970s really proved that the kidneys were the cause of hypertension. And the way he did this was to do elegant transplantation studies in which he would take a rat with hypertension, like the Dahl salt-sensitive rat, and he would transplant its kidney into a normotensive rat, and that rat would suddenly become hypertensive. Likewise, if he took a normotensive rat and took its kidney and transplanted it into a hypertensive rat, then suddenly that rat would become normotensive. And so we knew that the kidney was the source of the hypertension. And since then, there have been over 6 different animal models published that have all shown that hypertension travels with the kidney. So it doesn't matter if your blood vessels are thickened, if you get a normotensive kidney and put into you, your blood pressure will fall. So if the kidney has such an important role in hypertension, the question is, how does it cause hypertension? What is the defect in the kidney that causes hypertension? And there have been three major theories. There's a genetic theory, there's a congenital theory, and there's an acquired injury theory. So the genetic theory has been promoted primarily by Rick Lifton, but it goes way, way back, decades in fact. And the theory is that perhaps you inherit a number of genes that affect your ability to excrete salt. And if you have a lot of these genetics, gene polymorphisms, that you get this polygenic response where you end up not being able to excrete salt as easily as somebody else, and you become hypertensive. And there's a lot of reasons to believe this is true. Rick Lifton made some major breakthroughs in medicine when he identified the causes of several rare types of hypertension. And they all seem to involve sodium and sodium excretion in the kidney. And what he was able to show is that in the collecting duct, in particular, there's a sodium channel involved in sodium reabsorption, and it's the epithelial sodium channel, and if it gets activated so that there is increased sodium reabsorption, you will develop hypertension. And he found this in 3 different diseases. In glucocorticoid remedial aldosteronism, cortisol is actually driving aldosterone production. And in syndrome of apparent mineral corticoid excess, cortisol is not being inactivated by this enzyme beta HSD, and instead will bind the mineralocorticoid receptor. And in Little syndrome, there's direct activation of the epithelial sodium channel. And so in all of these diseases, the unique defect is that the kidneys can't get rid of salt because there's increased sodium reabsorption in the distal aspects of the nephron, and therefore this led to the hypothesis that hypertension is likely due to defects in sodium excretion, that if you have genetic polymorphisms involving these pathways, you could develop hypertension. Now, the genetics are clearly important, and there's no doubt that if you do have genetic polymorphisms involved in sodium excretion, that it will influence your risk for hypertension. But unfortunately, as we've done more studies, it's become apparent that genetics can only account for 20% of the hypertension variation. So there's got to be another component driving high blood pressure. And in fact, identical twins should be 100% concordant for hypertension if it's a truly genetic disease, but they're not. So if one identical twin has hypertension, there's only a 40% chance that the other twin will also have hypertension. And so we now know that genetics cannot completely explain this disease, and certainly genetics cannot explain this dramatic epidemic rise in hypertension that has occurred in the last century. So the second hypothesis is the congenital hypothesis. This is the hypothesis that Barry Brenner presented over 10 years ago. And basically this hypothesis is based on the fact that low birth weight children have an increased frequency for hypertension as adults. And it was then shown that low birth weight is also associated with low nephron number. And so low nephron number might lead to an inability to excrete salt and an increased risk for hypertension. And this hypothesis is sometimes called the Barker-Brenner hypothesis, because Barker was the one who showed the relationship with low birth weight, and then Brenner proposed that the low birth weight could lead to low nephron number and thereby affect sodium excretion. And in fact, there's some pretty good evidence that this is a very good hypothesis, because low birth weight is associated with future hypertension. Low birth weight is associated with low nephron number. Low nephron number is associated with an increased risk for future hypertension in animal studies, and nephron number is even reduced in patients with essential hypertension. This shows an example of the relationship between birth weight and nephron number in a study that was published some years ago. A general relationship, not super strong, but a real one. And likewise, if you take a rat that's pregnant and you malnourish it during pregnancy by putting it on a low-protein diet, the pups will be born with low nephron number, and they'll have a little bit higher blood pressure than their mates, than their siblings, and that come from normal mothers, and they'll show salt sensitivity as they grow older. So there is some evidence that this is a real pathway. And then in the New England Journal, Eberhard Ritz published a very exciting paper in which they studied young men who were dying in car accidents who had hypertension, and they compared them to controls who died from car accidents who did not have hypertension. And they found that there was fewer nephrons in the fewer glomeruli in the patients with essential hypertension. So it looks pretty real that low nephron number is a risk factor for hypertension, and this seems to be a very real potential mechanism. But there are problems with this hypothesis as well. First off, the mechanism's not clear because you can remove a kidney from a person who donates a kidney and they don't immediately become hypertensive. So it's not just a reduction in nephron number that's so important. Secondly, how would the low birth weight explain this epidemic increase in hypertension over the last century? It's not like we're having millions and millions of more low birth weight infants. And then there's the problem that low birth weight can only account for about 20% of the hypertension variation. Look at this. This is a paper from Barker himself showing the frequency of hypertension based upon birth weight. And notice that, you know, if you're a small baby, you have a 29% chance of developing hypertension. But if you're a big baby, you still have a 24% of them will develop hypertension. So the variation of birth weight is only going from here to here. It's about 20% of the overall frequency of hypertension. So there's a lot of hypertension that occurs in big babies, and actually it's becoming more and more clear that birth weight is not that strong a risk factor for hypertension. So this leads to the question of what could be driving hypertension. And some years ago, we revisited the hypothesis that subtle injury to the kidney might be the cause of hypertension. We based this on the fact that actually if you do biopsies of patients with hypertension, their kidneys aren't completely normal. In fact, there's a lesion in the kidney that we call arteriolosclerosis, which means disease of the arterioles. It's not atherosclerosis, it's arteriolosclerosis, and it's disease of the small blood vessels, often associated with tubular interstitial ischemia. Now, many years ago, a paper was published in the 1930s that showed that if you had arteriosclerosis in your kidney, you had like a 90% chance of having hypertension. But if you had arteriolosclerosis in your spleen, there was no association with hypertension. So it seemed like there was something specific about the kidney. And this led Harry Goldblatt in 1940 to propose that the arteriosclerosis, or small vessel disease, in the kidney was the cause of hypertension. But he didn't know the cause of the small vessel disease. And so it was kind of an unfulfilled hypothesis. But he suggested that hypertension might be due to ischemia to the kidneys due to small vessel disease. Well, he was rebutted. And the reason he was rebutted was there was a nice paper in the New England Journal that looked at 1,300 biopsies of patients with hypertension, and 5% of them did not have small vessel disease. So how could small vessel disease be the cause of hypertension if it's not present in everyone? Secondly, it was felt that the vascular disease was likely secondary to the hypertension. and that under high pressure the blood vessels would thicken. And then Goldblatt had no mechanism to explain why the hypertension was developing, or the microvascular disease was developing. So we revisited this hypothesis, and we published a review on this in the New England Journal about 10 years ago. And I do want to point out that I had three major collaborators with me, and one of them is Bernardo Rodriguez Iturbe and Jaime Herrera Costa and George Schreiner. And Bernardo in particular, we're going to be talking a lot about his work in the next few minutes. Anyway, the question was, could Goldblatt be right? And in the early 1990s, when I was but a young researcher, I was infusing angiotensin II into animals. And my tech told me, hey, you know, take a look at this under the microscope. And we looked under the microscope, and we saw that the arterioles were developing disease, just like in essential hypertension. And suddenly I realized that I could do an experiment to determine whether or not Goldblatt was right. So specifically, what I decided to do was to give angiotensin II to some normal rats, create subtle kidney injury, where they get that small vessel disease. And of course, while they're getting the angiotensin, they're hypertensive. But then I stop the angiotensin, and I biopsy them. They have the small vessel disease, but now their blood pressure goes back to normal. But then I randomize them to high or low salt diet, and the rats that got the high salt diet became hypertensive, boom, just like that. And if I gave high salt diet to a normal rat, nothing happened. So I presented this at a national meeting, actually an international meeting, and those two doctors, Jaime Herrera and Bernardo, ended up going out with me. And they said, you know, that's a very clever experiment, what you did, but you have to do micropuncture. You have to understand what's going on with the hemodynamics before you can really say this is essential hypertension. So this is Bernardo on the left and the late Jaime Herrera in the middle. They were leaders in nephrology. Jaime basically started the Mexican Society of Nephrology, and Bernardo started the Venezuelan Society of Nephrology. And so Jaime went and did the micropuncture for us. And basically what he found was that compared to normal animals, these animals develop renal vasoconstriction. Even 6 weeks after the angiotensin has been stopped, they still have vasoconstriction and reduced renal plasma flow, the characteristic findings of essential hypertension. In fact, these animals completely look like essential hypertension. They had low renal blood flow, high renal peripheral vascular resistance, normal GFR, or just slightly depressed GFR, and they had all the features of essential hypertension. The kidneys looked like essential hypertension. It was totally cool. So we said, okay, well, if subtle renal injury can lead to salt sensitivity, how does it do it? And one of the thoughts came from Bernardo. He says, I think ischemic kidneys will want to hold on to salt. And if you're developing microvascular disease, maybe that's causing ischemia. It's bringing in chemotactic factors. There's some inflammatory response, and maybe the inflammatory response is driving the sodium reabsorption. And in fact, when we looked in the kidneys, we found evidence for low-grade infiltration of T cells and macrophages. Well, I doubted this hypothesis. I didn't really, you know, I said to Bernardo, it's great, you know, it may cause inflammation, it may cause injury, but I don't see how inflammation can drive hypertension. You know, but I'm willing to work with you on this. But this is your hypothesis, Bernardo. So Bernardo said, well, there's a new drug that just came out called mycophenolate. And why don't we give mycophenolate to these animals and see if we can block the development of hypertension? So we gave mycophenolate during the angiotensin II infusion, which did not affect the ability of angiotensin II to raise blood pressure. But when we biopsied the animals afterwards, they no longer had the vascular lesions, and they had no inflammation, and by God, they didn't develop hypertension. So even though they'd gotten the same regimen, we could block the development of hypertension. And then Bernardo went on and showed that, that these white cells in the kidney were expressing oxidants and also expressing angiotensin II. And again, when he showed this to me, I said, T cells don't make angiotensin II. But within 2 or 3 years, a whole series of papers came out in Journal of Immunology and everything showing that T cells are actually a source of angiotensin II. And since then, he's done some elegant studies to show that the T cells are expressing angiotensin II. So now we came up with the idea that ischemia could cause vasoconstriction, and that leads to salt retention somehow with inflammation and oxidative stress. And he, again, Bernardo called me up one night, and he says, how do you think this is happening? Well, I said, well, ischemia is driving chemotactic factors. Chemotactic factors are bringing in the T cells. And he says, well, what if the T cells are autoreactive? I said, you mean to like antigens expressed under ischemic conditions? You mean like an autoimmune response? I said, no, I think this is reactive immunity, not autoimmunity. But when we started looking, we found that there were the expression of de novo antigens. And one of them was heat shock protein 70. Heat shock protein gets induced in a variety of conditions. And heat shock protein 70 was induced in this model. And so he sent a fellow to my lab, and we took T cells out of the spleen. And we found that the T cells were reactive to the heat shock protein 70. And what's more, we even found antibodies to heat shock protein 70 in some hypertensive strains, such as the SHR rat. And this here shows how lymphocytes proliferate in response to heat shock protein 70, this little blip right there in these sensitized animals. In this case, it's the SHR rat. So then Bernardo said to me, why don't we tolerize the animals to heat shock protein 70? And I said, you think you're going to prevent hypertension by doing that? He says, well, let's just try. So we got a peptide that allowed us to tolerize the rat. And we were able to block the the delayed type hypersensitivity response to heat shock protein 70, which you inject the antigen. It's like a PPD test. So you inject it in the air, and it swells up, and you can measure the air swelling, and it was blocked by making the animals tolerant. And this is the incredible experiment. This is in the SHR rat that becomes hypertensive as it gets older. Here is animals tolerized to heat shock protein 70. They didn't get hypertension. Well, I was still a skeptic. So we did another model, and it turns out that we've been able to induce this hypertensive pathway many, many ways, but it always involves these microvascular lesions and interstitial inflammation. And one way is to give a drug that blocks nitric oxide synthesis. And if you give a nitric oxide synthase inhibitor like L-name, the animals get hypertension, and then you stop the L-name, the blood pressure comes back to normal, and then they become salt sensitive again. So that if you give them salt, they become hypertensive again. And we had shown we could block that hypertension with MMF, or mycophenolate, just like the other models. Well, he liked that model, so we decided to study it. And so these are animals that have gotten the L-name. The L-name's then been stopped, and now they have salt-sensitive hypertension. And when we looked, they had HSP70 expressed in their kidneys, and their lymphocytes were proliferating in response to it compared to a control or tolerized animals. And when we took the cells out of the kidney, we could actually see a clonal expansion of those T cells reactive with heat shock protein 70. Or actually, this was out of the spleen. So we tolerized these animals in this model to heat shock protein 70, and we could block the T cell infiltration and the macrophage infiltration into the kidney, just slightly but significantly. And when we did that, we again could prevent the development of salt-sensitive hypertension. So here's salt-sensitive hypertension. These animals have had the microvascular lesions induced, and then they've been put on a high-salt diet. If you tolerize them, they don't become hypertensive. So then Bernardo said, I'm going to try to I'm going to give tolerized cells to these animals. So he tolerized some rats, then he took the T cells out of those rats, and then he injected it into hypertensive rats. And he also injected control T cells or B cells that have been tolerized. And nothing works unless you give a T-tolerized cell. But as you tolerize T cells to heat shock protein 70, you inject it in these rats, the blood pressure falls. It was getting too strong. We did it a variety of models. We did the SHR rat. We did this model. We also, like, you can induce hypertension following acute renal failure in rats, and we did it to that model. We even induced heat shock protein 70 in normal rats, and then gave reactive T cells, and they became hypertensive. So then Bernardo said, let's look at humans. This is amazing data that I'm going to present to you. I mean, this is, the paper is published. It was published last month in American Journal of Physiology. Should have been published in Nature. But the data shows that T cells from patients with hypertension are reactive to heat shock protein 70. So there's also antibodies in people with essential hypertension to heat shock protein 70. Heat shock protein 70 polymorphisms have just been linked with hypertension. So this may turn out to be a pretty important pathway. He also, Bernardo, did a study where he gave MMF to people who have psoriasis. So MMF is now being used to treat psoriasis. So he said, well, I can't really ethically give MMF to people with hypertension, but because it's an immunosuppressant, but why don't we study patients with psoriasis who have hypertension? So he got approval. So these were psoriatic patients who were going to get MMF anyway. And when they got the MMF, their blood pressure fell. When the MMF was stopped, the blood pressure came back up. And there was a relationship looking at urinary TNF-alpha falls when you get MMF, as does the blood pressure. Pretty interesting stuff. Well, why doesn't MMF treat hypertension in the transplant patient? Well, it might actually. But you know, you've got a lot of issues in the transplant patient where the renal function's reduced. So there's going to be a defect in salt excretion independent of any inflammation. You also have drugs like cyclosporin, which cause vasoconstriction and inflammation. And so you're countering all these effects. So it's complicated. So to finalize the talk, we'd like to suggest that a variety of mechanisms, and including our work, hyperuricemia seems to be part of this, induces microvascular lesions in the kidney, which causes inflammation and oxidative stress, and leads to sodium retention and hypertension. There is intriguing data that is developing suggesting that that inflammatory response may involve an autoimmune response. When we first presented our work on this, we were laughed at, basically. In the last 5 years, as you may know, studies by Harrison and others have shown that mice that lack T cells are protected from hypertension. And now it's become one of the hottest topics in hypertension research. I sit on the study section at the NIH, on the hypertension study section. Literally half of the grants coming in are trying to figure out the role of T cells in hypertension that Bernardo basically initiated when he said to me, I think it's the inflammatory cells, and I said no. So I want to thank a lot of people who've been involved in these studies, but in particular, I want to thank Bernardo Rodriguez-Iturbe and Jaime Herrera, George Schreiner, and thank you for your attention.
Thank you, Professor Richard, for this elegant talk, and we have time to take for 2 or questions or comments.
I will say, you know, we're not ready to be treating hypertension with immunosuppressive agents. And I think this is more trying to understand the cause of hypertension than to develop new treatments based on these pathways.
Any questions? Professor Jamal.
Yes. Yeah. Yeah.
And without them, you don't get control of the hypertension.
Yeah.
What was your comment?
Yeah, so like, for example, acute lupus nephritis can be associated with such severe hypertension. And you give them pulse steroids and all these different treatments, and the hypertension is still very severe, and you can give them multiple antihypertensives. Sometimes we've actually had to dialyze them to get the blood pressure under control, even when their GFRs are not so low. And the problem is that they have renal dysfunction, and they really have a defect getting rid of salt. And they have this generalized inflammation causing just terrible vasoconstriction. So my belief is that that the number one, the inability to get rid of salt is the primary problem. And if you have poor kidney function, that in itself will lead to hypertension. And if you have acute nephritis and your GFR is poor and you're filtering very poorly, that's going to cause hypertension. And who cares about the autoimmune response? But in a person with normal GFR, it looks like this autoimmune response could be important. I don't know how important it is. I mean, most of my work is focused on toxins like uric acid and sugar and so forth. But it's interesting that there probably is an autoimmune component to some hypertension that we don't really appreciate. And we're going to learn more about how important it is over the next decade.
تفضلي دكتور.
Did you have any studies about the heme oxygenase and carbon monoxide and nitric oxide affecting this model of hypertension? Heme oxygenase and carbon monoxide and nitric oxide.
The carbon
Yes.
Carbon?
Carbon monoxide.
Oh, carbon monoxide.
Yeah.
Yeah, that's there are some very interesting studies related to heme oxygenase, which is an enzyme that can make carbon monoxide and bilirubin or biliverdin, I guess. Heme oxygenase probably has a very significant role in the renal injury and the vasoconstriction. It is a protectant. It protects the kidney from oxidative stress. And when in these models, the way the white cells are working is there's this intense oxidative stress going on in the kidney, and there's an activation of the intrarenal angiotensin system. And heme oxygenase really does protect against that, whether it's the carbon monoxide or hydrogen sulfide. There's another one. I don't know, but heme oxygenase is really important. I'm convinced.
Any other question or comment? Then thank you, Professor Richard, and we move to the next speaker.
I have the honor to introduce Professor Volker Nicolet. He is a professor director of the Division of Nephropathology and Nephropathology Training Program. He is specialized in diagnosis and specific evaluation of kidney diseases. His major interest centers on different aspects of renal allograft pathology. Professor Volker has defined a new disease entity affecting renal allograft. This is BK virus nephropathy. He introduced surrogate marker into clinical practice for improved patient management. His future studies will focus on better identifying risk factor for developing BK virus nephropathy. Professor Walker, please.
Thank you so much for the kind invitation, and I'm happy to participate in this year's Congress here in Cairo. We will shift gears now totally, and I will focus on a complication that is mainly seen in renal transplants, that is polyomyelitis nephropathy. I'm of course fully aware of the fact that not everybody here in the audience has seen a case so far, but believe me, with the new immunosuppressive drugs of high potency, you will sooner or later encounter a case, and I hope that at that juncture some of the aspects that we will discuss today will come handy in patient management. During my talk, I will use this abbreviation so that you know what I'm talking about. PVN stands for polyomavirus nephropathy. And here are the culprits that can cause disease. Polyomaviruses on the left hand in a negative electron micrograph are 40 to 50 nanometer double-stranded DNA viruses that are not encapsulated. Polyomavirus nephropathy nearly exclusively occurs in the setting of renal transplantation and in the renal allografts. There are only about 2 handful of more or less large case reports, small series reporting disease in native kidneys. And having said that, there is already one pearl of wisdom right here. That means that solid organ transplant recipients other than kidney transplant recipients, meaning patients with lung transplants or heart transplants, hardly ever develop polyomavirus nephropathy in their native kidneys. So we're really looking at something that occurs in the renal allograft. The disease is mainly induced by the replication of one particular polyomavirus strain called BK virus. JC virus and SB40 virus is only infrequently found, and infrequently found as the major driving force of the disease process. Now, these are the few topics that I will touch upon over the next 35 minutes or so, and let us first start with some general background information and potential, and the emphasis here is on potential risk factors associated with disease. And these are, of course, spotlights I want to shed on these aspects that I believe are important. We will jump around a little bit, so I hope that you will stay with me, and I try to make it as logical at this juncture as I can. Now, one aspect to keep in mind is that talking about polyomavirus nephropathy means that as of now, we believe that this is a disease that is caused by the reactivation of latent viruses that come in the donor organ. It is something that sits in the donor organ and is being transplanted. So we are more or less looking at a ticking time bomb that is transplanted each time. And the question arises then, how often do we, in the general population, and all of us sitting here, how often do we find latent BK viruses in our kidneys, and thus in the general pool of donor organs? And the answer is that in about 35% of healthy kidneys without any evidence of disease whatsoever, you find evidence of latent BK viruses. And in 9% to 24%, these are relatively high viral loads. And the raw data that we collected a couple of years ago are listed here. In the first row, you see that 20 of 58 healthy kidneys, normal kidneys, showed evidence of latent BK virus, and that is evidenced by PCR analyses. You see in the middle that 14 of 58 cases, that is 24%, had evidence of latent virus in different spots, different areas of the healthy kidney. And in 9%, that is a row below, these viral load levels were relatively high, defined as more than 1,000 BK copies per 25,000 cell equivalents. So there is a certain pool of donor organs or of healthy organs that carry a latent virus without evidence of disease whatsoever. So every third person in this room has latent BK virus in the kidney. Question is, how does the latent virus get to the kidney? The answer to that is very simple, and I'm sure most of you know that primary infections with polyomaviruses are very common in children between the age of 4 and 8. These infections, primary infections, are asymptomatic or run with non-specific signs of an upper respiratory infection. Now, after that primary infection, and that is the crucial step here, the virus is not eliminated from the healthy individual, the healthy body, but establish latency in a significant percentage of cases, and primarily in the urogenital tract, meaning in urothelial cells, transitional cells, and in the renal tubular cells, and that is, of course, where we could amplify it by PCR in our study. All these latent infections, just keep that in mind, are asymptomatic. They do not cause disease. However, once in a while, latent infections in healthy individuals can be transiently reactivated, and we'll get back to that in a little while. Now, what about the antibody response in the setting of primary infections and latent infections? And that is, I think, one interesting aspect, that in children, practically all children at the age of 10, 12 have circulating antibodies against polyomaviruses and against BK virus, and you see the number here. It's found in around 90 to 100% of young individuals. Now, that changes later on during adulthood, and the frequency here is lower, 46 to around 90%, meaning that not all adults have circulating antibodies against polyomaviruses. And the question is, of course, is it possible, is there some evidence that these patients, these recipients with potentially low levels of antibodies are more prone for viral replication and viral infections? We know very little about it, and what I'm going to show you here are some animal data that we recently collected, and we're very excited about it. So the question here is, how do polyomavirus antibodies control polyomavirus replication? And in conjunction with that question, does the status of the kidney, the injury of the kidney, the development of the kidney have something to do with the ability of replication of polyomaviruses? Now, we studied that, and these studies are ongoing in a mouse model, and what we found is summarized here. Number one is in mature kidneys, healthy kidneys, in adult mice, polyomavirus nephropathy never develops. You can inject mouse polyomavirus, nothing will happen to these mice, irrespective of circulating anti-polyomavirus antibodies. So the status of the differentiation and the degree of injury of the kidneys play a role in the development of polyomavirus nephropathy in the setting of transplantation. Now, in contrast, developing organs, developing kidneys, injured kidneys, show polyomavirus nephropathy in the absence of circulating anti-polyomavirus antibodies. So if the organs are immature, injured to some degree, and antibodies are not present in these animals, polyomavirus nephropathy develops. That can be blocked by the existence of circulating antibodies. So there, the antibodies in this scenario give a protective umbrella and protect from disease. Now, if polyomavirus nephropathy in these animals exists and is ongoing, persistent, then high antibody titers, developing high antibody titers, do not really cure, eliminate polyomavirus nephropathy rapidly. Maybe these antibodies at that time point can ameliorate the disease course. We don't know that yet, but at least the antibodies are insufficient for really healing polyomavirus nephropathy rapidly, and that is important when we get to therapy options later on. Now, last not least, and this is of course a little jump in our scenario here, what else could contribute to the onset of polyomyelitis nephropathies that we see, at least in Western countries like the US and Europe these days? And of course, what is the role of immunosuppressive drugs? Nobody would have invited me to talk about it 25 years ago, because in the early 1990s and in the 80s, polyomyelitis nephropathy was not seen. Of course, we were transplanting patients there. Of course, the patients were immunosuppressed, but polyomyelitis nephropathy was hardly ever reported. Now, that changed in the mid-1990s, and primarily due to the fact that new immunosuppressive drugs were given at that time, first and foremost high-dose tacrolimus. And that, of course, was propagated, among others, by Pittsburgh, that introduced tacrolimus into the regimen very early in the 1990s. And Pittsburgh was the first center that reported a large series of polyomyelitis nephropathy in the mid-1990s. Before then, the rest of the world followed and experienced the same. So there is good evidence right now, and I don't want to really go into the details, that tacrolimus trough levels of 6 to 8 nanograms per milliliter and larger are associated with an increased risk for the development of polyomyelitis nephropathy. And that means the risk factor is increased by 2 or 3 or 4 times to develop polyomyelitis nephropathy. Now, how can we put everything together at this moment? Number one is it seems that the donor organs must have latent BK virus at time of transplantation, and presumably even high latent BK virus loads predisposed for the development of viral nephropathy later on. And it also seems that there is some evidence that if the recipient has low levels of circulating anti-BK virus antibodies, that will also contribute to more easy viral replication once the whole risk scenario is established. But of course, that is not enough in it by itself. So hit number one that can really be contributing here is high immunosuppression with tacrolimus greater than 6 to 8 nanograms per milliliter over a long period of time. And this would not be enough. This cannot explain why polyomyelitis nephropathy is not seen in cardiac graft recipients in the native kidney. So something else must come and must be specific for the renal allograft, and that is here hit 2. We got some evidence from the mouse data that an immature state, a form of injury, tubular cell replication, mitoses in the